All right, for our last example, I'm going to use a new data set that I have posted on the website that has data from states. So basically for a list of 10 states, we have 3 different variables measured for them that I pulled information from the US Census. So I don't have listed which states these are. But I actually knew which states these were. So like the first one on there is Pennsylvania, and then there's Virginia, South Carolina, Alabama, Texas, Illinois, North Dakota, Arizona, California, and Washington. So I tried to pick states from all around the country. And so the first column is the proportion of residents that have a college education. Now, this data is about 10 years old, but it hasn't changed that much. The second is the mean household income. And the third column is the proportion of residents that are over age 65. So I figured that if a state had more people with a college education, then I would expect them to have a higher mean income, because presumably more college educated people, there'd be higher paying jobs. I don't know. I'm just guessing, right? And if there was more with a college education, what would it mean about how many there were over 65? I don't really know, actually. Um, you know, a long time ago, fewer people went to college, but by the time that people who are in their 60s and 70s, they would have been college aged in like the 1960s or 1970s, and college was starting to get popular then, I think. College sort of boomed in popularity after World War II with the GI Bill. So I don't know what the association might be with the over 65 column, but I would expect these two to sort of go up together and go down together. When 2 variables sort of go up together and go down together, that's called a positive correlation or association. And then there's a negative correlation if when one goes up, the other goes down. So that might happen sometime. So maybe we'll be in a situation where a higher proportion college means a lower proportion over 65 for whatever reason, and then that would be a negative correlation. We won't know until we run the numbers. So let's try running linear regression using these first 2 columns, proportion with college and the mean income. So regression, fitted line plot. We'll get rid of these numbers from the previous example. We'll put proportion with a college education in the x-coordinate, and we'll put the mean income in the y-coordinate. So we'll hit OK, see what we get. So this actually has a really good R-squared. Our R-squareds were terrible on the exams, but this one's 93%. So if you know the proportion with college in a state, and you try to use this formula up here to guess their mean income, you should get a pretty good answer, at least based on the, like 10 data points isn't a lot, but you can see they're pretty well in a line. Like these ones are definitely lower in both variables. These are higher in both variables. They line up pretty well. 1, 2, 3, 4, 5, 6, 7 of these are pretty close to the line. These ones are kind of close to the line. This one's a little far away. So that 266 and 61. Which state was that? Let me just look that up. 26. That's California. So they have a high proportion in college, but only a slightly high mean income for whatever reason. And yeah, they're as much in a line. They're way more in a line than our previous examples. So just to extend this example a little bit further, I have some other states here where I know their college proportion. So for example, Kansas has a college proportion of 0.258. So let's try to guess what their mean income is. So I'm going to flip over to Word so that I can write some of this stuff down. So where's my Word? Okay. Share. Yeah, so we're on to our states example. So right now we're comparing proportion with college to mean household income. And this is the formula we got from Minitab. Okay, so Kansas has 0.258 with college. That's their proportion with college, 25.8%. So let's guess the mean household income. So the way I would do this is I would just plug 0.258 into the proportion with college spot in the equation, and then I would say that mean income is approximately, so this is a guess, so we'll say that it's approximate, 5.557 plus 1.93.8 times 0.258. So I'm going to pull up my calculator. I'm not going to share my calculator screen so you won't see this, but let me just quickly type in 193.8 times 0.258, and that's about 50, and then we add on 5.557. This comes out to 55.5574. 55.5574. Okay, so that is our guess for what their mean income is. So I actually happen to know the actual answer. So the real answer, let me change back to my standard font size here. So the actual mean income for Kansas was 50.2. So that's thousand. So this is 55,000 was our guess. 50.2 thousand was the actual answer. So we were off by 5,000, which is a pretty big chunk, because if you look at the data, all the numbers were just sort of in the 40s and 50s with a few in the low 60s. So like we guessed that they were sort of like towards the upper end of what we had seen, and actually they were more in the middle. So our guess wasn't great, but maybe Kansas was a bit of an aberration. But that's how you would use this formula to guess things if you wanted to. Before we shut off this example, and I think that like before we call it a day, why don't we just run one more quick example using this same data. So how about we run proportion with college and proportion over 65? So regression, fitted line plot, let's get rid of this mean income, and we'll do proportion over 65 just to see what we get. Okay, this had a terrible R-squared, worst one of the day. It did have something new. This line is sloping downwards. So there's a little bit of trend. If you sort of ignore this point down here and these 2 points up here, then the rest of them look like they're in a line. But these 3 points, that's 3 out of 10 that are way out of the pattern. So that was enough to make our R-squared very small. But this is a downward sloping line. There's a negative on the slope here. So that's a negative association. And it means that as proportion of college is going up, if there's any pattern at all, it's that the proportion over 65 is going down. It's not a very strong pattern at all, but like the little bit of pattern that there is that when one goes up, the other goes down. Okay, and we still have these dotted and dashed lines where we're estimating where the mean would be for each of these numbers, and the dotted line are supposed to capture 95% of all numbers. If the more these dots were in a line, like the more there was a pattern, then the tighter these dotted lines would be. You know, the fact that they're really spread out is just because the data is actually quite spread out and the association is small. Yeah. Was the lines any tighter here? Yeah, so the lines were much tighter when we had a higher R-squared. When we have a lower R-squared, the lines are much more spread out. So here they're tighter because there's just a tighter pattern overall. Okay, so I think that's enough for today. I have one more day that I want to talk about linear regression, and then we'll do some review days, and that'll be the end of the semester. So that's it for today.